The Apollo astronauts lied to us. Not about the science, not about the moon. They lied about what was actually up there. For decades, the men who orbited and walked on the lunar surface came home and described, in careful, measured, military pilot language, a grey, dead world. A museum piece, geologically simple, thoroughly understood. The data backed them up. Thousands of photographs, spectral analyses, topographic scans, all of it pointing to the same conclusion. The moon is a quiet, predictable place where nothing has happened in 3 billion years and nothing will happen for 3 billion more. They weren't lying on purpose. They were repeating what their instruments told them, what the culture of the program expected them to say, and what 50 years of robotic orbiters seemed to confirm. But on April 6, 2026, 4 astronauts flew within 4,000 miles of the surface aboard the Orion spacecraft and immediately started seeing things that didn't match. Colors that shouldn't have been there. Topography that photographs had completely failed to convey. Flashes of light on the darkened surface that made scientists in Houston literally scream. And a bright, swirling pattern visible from Earth with a backyard telescope that, after 4 centuries of observation, still has no confirmed explanation. The Artemis II crew didn't just fly around the moon. They caught it in a lie that every previous mission had missed. Reed Wiseman, Victor Glover, Christina Cook, and Jeremy Hansen spent 7 hours circling the moon aboard the Orion spacecraft, named Integrity by the crew. They carried a fleet of Nikon cameras, a set of eclipse glasses, and roughly 2 years of geological training, courtesy of David Kring, a planetary scientist who had spent decades studying the lunar surface from photographs. Kring had trained them to look for specific features, specific color gradients, specific structural clues that cameras from orbit can capture but cannot interpret the way a trained human eye can. The distinction matters more than you'd expect. A camera records light. A brain connected to a pair of eyes notices when something is wrong. The crew worked in shifts. Because window space in the Orion capsule is limited, only 2 astronauts could observe at a time, so they rotated in pairs, each team taking between 55 and 85 minutes at the windows before swapping with the other pair who had been exercising or working on other tasks. They used camera shrouds, essentially black curtains with holes cut for the lens, to prevent cabin light from reflecting off the window panes and contaminating their photographs. It was meticulous, unglamorous work, the kind of thing that doesn't make headlines but determines whether the science is usable. One of the first targets on their observation list was the Orientale basin. If you haven't heard of it, that's because it sits right on the boundary between the near side and the far side of the moon, in a position where it's almost impossible to see clearly from Earth. Apollo astronauts caught glimpses of its outer edge, fragments of a ring structure too large to take in from their flight paths. No human had ever seen the full thing. Orientale is nearly 600 miles across. It formed 3.8 billion years ago when something massive, likely an asteroid several dozen kilometers wide, slammed into the lunar surface with enough energy to liquefy rock hundreds of kilometers deep. The impact punched through the crust and created a multi-ring basin so geometrically precise that scientists have called it the Grand Canyon of the Moon. From orbit, the concentric mountain rings look like a bullseye pressed into stone. Wiseman described the innermost ring, the annular structure that defines the basin's center, as looking like a pair of lips or a kiss on the far side of the moon. Then he paused and corrected himself. It was far more circular than he remembered from training images. The northern section was wider and darker. The southern section was lighter. The proportions, the symmetry, the sheer scale of it, none of it translated properly from flat photographs into 3-dimensional reality seen through a window at 4,000 miles. This was a recurring problem throughout the flyby. Hansen, the Canadian astronaut, put it most directly after the mission. The thing that shocked him most was the three-dimensionality of the moon. On paper, on screens, in every simulation they had run, the surface looked like what it technically is, a sphere covered in craters. In person, from the vantage point of a spacecraft moving through lunar space, the elevation changes hit differently. Kring, listening from the science evaluation room at Johnson Space Center in Houston, had been trying for years to communicate this exact point. The elevation differences near the moon's south pole are greater than the height of Mount Everest on Earth. Flat images on flat screens cannot convey that. He could hear Victor Glover finally getting it. Glover, for his part, couldn't stop talking about the Terminator. Not the movie. The Terminator is the line dividing the illuminated half of the moon from the half in shadow, the boundary between lunar day and night. Along that line, sunlight hits the surface at such a low angle that every bump, every ridge, every crater rim casts a shadow 10 or 20 times its own height. Glover called it the most rugged thing he had seen from a lighting perspective. He described islands of light surrounded by valleys that looked like black holes. Pockets of terrain so deeply shadowed they appeared to be missing from the surface entirely. Kelsey Young, the mission's lunar science lead, told him afterward that those observations, the way he described the interplay of light and depth and structure, were exactly the kind of thing that human eyes contribute that no camera can replicate on its own. The reason comes down to how trained observation works. A camera captures reflected light at fixed wavelengths. It records brightness and color within the limits of its sensor. A human brain, connected to eyes that have spent months learning what specific minerals look like under specific lighting conditions, does something fundamentally different. It compares. It notices when a shade of brown shifts slightly toward blue in one section of a crater wall. It registers that the floor of a basin is a different hue than the rim. It catches subtle gradients that a digital sensor records as noise. Young explained the difference with a sandbox analogy. Shine a flashlight directly on top of a sandbox and you'll see the color of the sand. Move the flashlight to the side and you lose the color entirely. But now you can see every ripple and ridge in the surface. The Artemis II crew got to watch both effects in sequence as the spacecraft moved through its flyby path, seeing the same terrain under changing angles of illumination, catching color details and topographic details that had never been observed together by human eyes. The colors they reported were not what anyone expected. The crew described shades of brown and green on the near side of the moon, distinct color variations across crater walls and lava plains. These variations correspond to mineral composition. Iron and titanium deposits in the lunar soil produce subtle shifts in reflectivity that look nearly identical in orbital photographs, but separate into distinct hues when viewed directly. The astronauts were, in effect, doing geological fieldwork from 4,000 miles up, spotting mineral boundaries that orbiters had hinted at but never confirmed with this kind of granularity. Then there was Reiner Gamma. Reiner Gamma is one of the strangest features on any body in the solar system, and it was on the crew's observation list specifically because nobody understands what it is. It sits in Oceanus Procellarum on the near side, a bright, swirling pattern spread across roughly 60 kilometers of otherwise dark basalt plain. First spotted through primitive telescopes in the 1600s, it was originally misidentified as a crater. Detailed observations from orbit eventually proved it casts no shadow. It has no topography at all. It is completely flat. The swirl pattern is purely an albedo feature, a difference in how much light the surface reflects, painted across terrain that is otherwise physically identical to its surroundings. What makes Reiner Gamma genuinely strange is what sits beneath it. The swirl is co-located with a magnetic anomaly, a pocket of magnetized rock in the lunar crust that generates a localized magnetic field strong enough to form a miniature magnetosphere stretching 360 kilometers across the surface. The Moon has no global magnetic field. It lost that billions of years ago when its core cooled. But scattered across the crust, there are these remnants, fossil magnetic fields locked into rock that solidified when the Moon still had a functioning dynamo. Reiner Gamma's pocket field is strong enough to deflect incoming solar wind particles, and the leading theory is that this deflection is exactly what created the swirl. The solar wind, that constant stream of charged particles from the Sun, slowly darkens exposed lunar soil over hundreds of millions of years through a process called space weathering. Where the magnetic field shields the surface, the soil stays bright. Where the field has gaps or cusps, solar wind particles concentrate and darken the soil even faster than normal. The result is a pattern of bright and dark lanes that traces the shape of the magnetic field itself, like a tan line on skin that was partly covered by an oddly shaped piece of fabric. Except it doesn't fully work. The magnetic anomaly doesn't align neatly with the geological structures around it. Unlike similar features on other parts of the Moon, which sit on the exact opposite side of the globe from major impact basins, Reiner Gamma has no corresponding impact origin. One hypothesis is that a comet struck the surface and somehow magnetized it during the collision. Another suggests a buried, uniformly magnetized elliptical disk beneath the surface, possibly from an extremely oblique impact that grazed the Moon at a shallow angle. A third theory proposes that fine dust particles, lofted by micrometeorite impacts, were sorted by the local magnetic field into the bright swirl pattern. None of these hypotheses have been confirmed. A future mission called Lunar Vertex, led by Johns Hopkins Applied Physics Laboratory, plans to land directly on Reiner Gamma and drive a rover across it to measure the magnetic field and soil properties at ground level. Until that mission flies, Reiner Gamma remains one of the Moon's genuinely open questions. The Artemis II crew observed it as part of their near-side flyby, noting its brightness against the surrounding mare. Their photographs and color observations will be compared against orbital data to see whether human eye detection reveals gradients or boundaries that instruments missed. It's one data point in a much larger investigation, but it's the first time trained human observers have looked at Reiner Gamma from lunar space in over half a century, and the first time anyone has looked at it with the specific intent of mapping color and albedo variation at this resolution. Halfway through the flyby, the Moon passed between the spacecraft and the Sun. From the crew's perspective, the Sun slipped behind the lunar disk and disappeared. The corona, the Sun's outermost atmosphere, bloomed around the Moon's edge in a ring of ghostly white light. From Earth, a total solar eclipse lasts a few minutes at most, because the Moon and Sun appear almost exactly the same size in the sky. From 4,000 miles behind the Moon, the geometry is completely different. The Moon was close enough and large enough to block the Sun for nearly 54 minutes, almost an hour of totality. No human being had ever witnessed a solar eclipse from this vantage point. The crew put on eclipse glasses during the partial phases, making them the first people to use eclipse viewers at the Moon. Once totality began, they removed the glasses and looked directly at the scene. Wiseman called it an absolutely spectacular, magnificent experience. The photographs they took during totality show the dark lunar disk surrounded by a glowing halo. NASA's science community is still investigating that halo. The initial assumption was that it's the solar corona, but preliminary analysis suggests it may include contributions from zodiacal light, the faint glow caused by sunlight scattering off interplanetary dust particles spread along the plane of the solar system. Distinguishing between the two from these images could provide data about dust distribution in the inner solar system, a measurement that is extremely difficult to make from Earth's surface. Stars appeared: Venus, Mars, Saturn, Mercury, all visible alongside the corona, which is normally washed out by the sun's brightness, but was now the only source of direct light. Earthshine illuminated the near side of the lunar surface in a pale, reflected glow, sunlight bouncing off our planet and landing softly on the moon. Glover compared the solar streamers radiating from the corona to the spotlight on top of the Luxor Hotel in Las Vegas, then immediately took it back. This looks like what that wants to be when it grows up. And then, in the darkness, the moon started flashing. 6 times during the eclipse, the crew saw brief points of white to bluish-white light appear on the darkened lunar surface. Each flash lasted less than a millisecond. Wiseman said they were as fast as a camera shutter opening and closing. The flashes were meteoroid impacts, small rocks, larger than dust but smaller than a boulder, slamming into the surface at tens of thousands of miles per hour and vaporizing on contact. On Earth, objects that size burn up in the atmosphere long before they reach the ground. On the moon, there is nothing to slow them down. Every particle that approaches the surface arrives at full speed and leaves a permanent scar. In the science evaluation room at Johnson Space Center, the reaction was immediate. Kelsey Young reported audible screams of delight from the scientists monitoring the crew's observations. They hadn't expected the astronauts to see this many impacts. The crew had been trained to look for them, briefed on what they might see, but the expectation was maybe 1 or 2 flashes, if they were lucky. 6 was extraordinary. Jenny Gibbons, the mission's backup astronaut, told reporters that impact flashes are something we have not witnessed often, and that 4 or 5 sightings was outstanding for a single observation window. The implications are practical, not just scientific. If NASA intends to build a permanent base on the lunar surface, which is the stated goal of the Artemis program, then the frequency and size distribution of incoming meteoroids matters enormously. On Earth, the atmosphere provides a shield that disintegrates small impactors before they become a threat. The moon has no such shield. A rock the size of a marble, traveling at 40,000 miles per hour, carries enough kinetic energy to puncture a habitat wall. Peter Schultz, a professor of geological sciences at Brown University, said after the mission that the Artemis II observations show the daily flux of meteors should be monitored more closely before a lunar base is established. Understanding the rate of impact, the size range of the objects, and the geographic distribution of strikes is not abstract science. It is engineering data for keeping people alive. NASA's ground teams are now working to correlate the crew's visual observations with data from the Lunar Reconnaissance Orbiter, which was circling the moon at the same time. Before launch, NASA had also invited citizen scientists around the world to monitor the moon with backyard telescopes and record any impact flashes they spotted, specifically so those Earth-based observations could be compared with what the crew saw from the other side. The cross-referencing of those datasets, human eyes at 4,000 miles, robotic cameras at 100 kilometers, and amateur telescopes at 240,000 miles, will produce the most complete picture of lunar impact activity ever assembled from a single observation window. The crew also photographed the South Polar region in detail. This matters because the South Pole is where NASA wants to land astronauts on future Artemis missions. The area is pockmarked with permanently shadowed craters thought to contain water ice, a resource that could be critical for sustained human presence. It is also far more rugged and dangerous than the equatorial regions where Apollo astronauts landed. The Artemis II photographs of the South Pole's terrain, taken from angles and lighting conditions that orbital cameras don't always capture, will help planners evaluate potential landing sites with a level of context that data alone cannot provide. Northwest of Orientale, the crew observed Hertzsprung Basin, a nearly 400-mile-wide crater on the far side. Hertzsprung is older than Orientale, and you can see that age in its structure. Where Orientale's rings are sharp and geometrically clean, Hertzsprung's have been battered and eroded by billions of years of subsequent impacts. Its double ring of mountains is still visible, but degraded, softened, punched through in places by newer craters that landed on top of the older wound. By comparing the two basins side by side, observing one young and well-preserved and the other ancient and battered, scientists can begin to reconstruct how lunar features evolve over geological timescales. The crew's photographs of Hertzsprung's concentric rings, captured under low-angle illumination that emphasize the worn topography, are among the first direct human observations of this structure. On the near side, before the spacecraft swung around to the far side, the crew also observed Glushko crater, a bright 27-mile-wide impact site known for the white streaks that radiate outward from it for up to 500 miles across the dark mare surface. Those rays are ejecta, material blasted outward during the impact and deposited in long streaks that haven't yet been darkened by space weathering. Their brightness tells scientists the crater is relatively young by lunar standards, though young on the Moon still means tens or hundreds of millions of years old. Throughout the observation window, the crew also looked for lobate scarps, low ridges on the surface that are the visible expression of tectonic faults. These faults formed relatively recently in geological terms, caused by the Moon's interior slowly cooling and the entire body contracting like a drying fruit. The scarps are potential sources of moonquakes, and understanding where they are and how active they might be is critical for deciding where to build structures that need to survive for years or decades. 7 hours after the observation window opened, it closed. The crew packed up their cameras and began the journey home. They carried with them roughly 10,000 photographs, hours of recorded verbal descriptions, and a set of observations that scientists at Johnson Space Center are still processing weeks later. The flyby did not involve a landing. Nobody walked on the surface. Nobody collected a rock. Nobody planted a flag. What the Artemis II crew did was something quieter and in some ways more important. They looked. Carefully, systematically, with trained eyes and calibrated instruments, they looked at the Moon the way a geologist looks at an outcrop, not for the big picture, but for the details that don't fit, the colors that shift where they shouldn't, the shadows that reveal what flat images hide, the flashes of light that tell you the surface is under constant assault from objects you can't see until they hit. For 53 years, we studied the Moon through screens. We analyzed it through algorithms. We mapped it with lasers and radar and spectroscopes, and we built a model of a quiet, predictable, thoroughly understood world. The Artemis II crew spent 7 hours proving that model is incomplete. The colors are wrong, or at least more complex than our instruments suggested. The topography is more dramatic than photographs convey. The surface is being reshaped by impacts more frequently than expected. And one of the most visible features on the near side, a bright swirl you can see from your backyard with a decent telescope, remains a genuine mystery that no one can explain. The Moon is the closest thing to us in space. It is 240,000 miles away. We have been staring at it since before we were human, and after all that time, after all those missions and all that data, 4 people flew there with cameras and their own eyes, and the first thing they noticed was how much we missed. The photographs are still being processed, 10,000 images, most of them not yet released to the public. The verbal descriptions the crew radioed back during the flyby are being transcribed and cross-referenced with orbital datasets. The impact flash observations are being matched against lunar reconnaissance orbiter data and citizen science recordings from backyard telescopes around the world. It will take months, possibly years, to fully analyze what 7 hours of human observation produced. And when Artemis II lands astronauts on the surface, those crews will carry with them every lesson, every data point, and every unexpected discovery that the Artemis II crew brought back from their flyby. Not as souvenirs, as survival information. We thought we knew the moon. We had the data to prove it. Turns out the data was a rough draft. Thanks for watching, and I'll see you in the next one.